Yes, please. In the previous classes, we were describing the power flow analysis in the power system. We described the various methods of power flow analysis, including the Newton-Raphson method, then fast decoupled Newton-Raphson method, and later DC load flow DC load flow equation method for solving the power flow equations. Now, next is the if we apply the AVR, then how the power flow analysis will be performed. So AVR, you know, the role of the AVR is to maintain the constant voltage of the bus. Suppose there is 26 bus system and bus number 5, at bus number 5 if AVR is connected, then this AVR will try to maintain the constant voltage at that bus. Earlier we assumed what we were doing earlier while performing the power flow analysis, we assumed that since the role of AVR is to maintain the constant voltage, and how it is being done, because AVR is supplying the reactive power. So by supplying the reactive power, by absorbing the reactive power, it controls the voltage of the system. Now, if it controls the voltage of the system, then earlier we, in the conventional method, we used to assume it as a PV bus. When P is 0 at AVR, P is 0. Active power is not there. Only that much amount of reactive power is supplied, and at which that much reactive power is supplied, which is required to maintain the constant voltage at that bus. So voltage P0 and V is, say, for example, we maintain 1 per unit, so it can be like a PV bus. But in the PV bus are the generator buses. Okay, PV buses are the generator buses, and generator buses, what are the limitation of the generator buses? Why they are called the generator buses as a PV buses? Because they supply the P, so the P is known, and they maintain the voltage. That's why V is known, and voltage is maintained by making the excitation control. By making over excitation, it can supply the reactive power. By making the under excitation, it supply the leading power. So by making the over excitation and under excitation, controlling that, we can control the reactive power input to the system, and by thus it control the voltage. So the voltage is maintained as a 1 per unit. But here, in the generator, you see, if later on we told, while we were performing the load flow analysis, then if some of the generator is not able to supply, because each generator having the maximum and minimum limit of the reactive power. Suppose your 100 MB, for example, 100 MB generator is there, and it has a limit of reactive power that plus minus 20 MVAR reactive power it can supply. But for example, for some purposes, if the reactive power demand from that generator bus is more than its limit, let's say limit is 20 MVAR, but as per the load flow, it is saying the reactive power requirement may be say 25. Then it cannot supply the 25 reactive power because its limit is only 20. Then what it will be? It will do that 20 amount of reactive power MVR will be continuously to supply, and then in place of PV it will be the PQ bus. Now, what is the difference between this and the static VAR bus? Here in the static VAR bus, you see this is the anti-parallel inductor and capacitor. Anti-parallel inductor and capacitor are connected, and anti-parallel thyristors are there. So why at some bus, if this static VAR compensation is correct, VAR means reactive, BA means volt ampere and reactive. So reactive volt ampere, reactive VAR can be supplied by from here by controlling this firing angle. If the firing angle is changed from here, then it is called thyristor control reactor. It is a reactor. By controlling the thyristor, we can allow the definite amount of reactance to be connected into the system. And by this thyristor switched capacitor means it can if one thyristor is switched, then one capacitor will be connected into the system. Another thyristor is switched, then another thyristor will be shown into the system. So number of thyristor may be in the parallel. Here it is shown only one, but in fact there can be number of thyristor which can be switched into the system. So depending upon the value of that capacitors, depending upon the requirement, there can be C1, C1, C2, C3, the effective amount of C, if they are in parallel, here they are in parallel. So if effective amount of C will be into the, effective amount of capacitor will be, capacitance will be into the system. And this is variable. This is variable inductance. So let it be fixed thyristor. After switching, it will be fixed. Then this can be variable thyristor. By varying this firing angle of this thyristor, we can vary the reactance. So once we can vary the reactance, net effect XL, this is XL, this is XC. So XL minus XC, net reactance will be there into the system. And this draw the, if overall reactance of the system is lagging, then it will draw lagging current. If overall including both, if it is a leading, means if it is more than it is less, then it will be leading. If overall is leading, then it will draw the leading current. If the capacitive in nature, overall capacitive in nature, then it will draw the leading current. Otherwise, it will draw the lagging current. So depending upon lagging or leading drawing of this, it can maintain the voltage to be. Suppose there is, later on we will show you, just it is like this. Say here it is a load is connected. If load is lagging in nature and it is taking leading current, so lagging and leading net compensation will be done such that, otherwise if it is not there and if it is a leading load, lagging load, so lagging I into this drop I x of the transmission line, I into x, there will be drop here, and this voltage was will be V. If the voltage of here it is say V, then V will be equal to or this say voltage of here is E or VG, generator voltage, or V1. So V1 minus I into x, this voltage will be there. I is the load current here. If this is the lagging current, if it is a leading current, net lagging and leading, net current may be such that if it is a suppose unity power factor, or depending upon, say, if it is leading net it can be lagging, lagging amount may be reduced, means if it is a 0.9 lagging and if it is a some 0.9 leading, the net effective will be, say, unity power factor, depending upon the value of this, magnitude of this, then I minus x will be less, and this voltage can be maintained as a constant. In this way, it is a working. Now, what is the difference between this and the generator buses? In the generator bus, we told it has the reactive power fixed, that minimum or maximum range. It will supply, if generator is not able to supply the reactive power demanded, then it will supply the maximum or minimum, depending upon whether it is on maximum side or it is working on the minimum side. It will supply that amount of fixed reactive power. But here, this SVS cannot supply that. It is not fixed that it will supply that amount of reactive power. This reactive power, the reactive power supplied will depend upon the value of susceptance, maximum value of susceptance. It can be, say, firing angle is such that the whole inductance is connected, or firing angle can be such that no inductance is connected. But even then, we cannot say how much reactive power will be supplied, because reactive power supplied will be the function of this voltage. Not only reactive power is V square by X, and X is varying, but V is not fixed. V is also not fixed. So reactive power will be V square by X, and we want to maintain a V as a constant. So we cannot assume as a V voltage of this bus as a constant. So it cannot be PV bus. Neither the reactive power supplied can be predetermined value as in case of generator. So this is the difference. That's why it is not absolutely good. It is not good to presume this bus as a PV bus. That's why now how then to incorporate this VAR as static VAR compensation system while doing the load flow study. This is to be seen. Now let us understand the working. Once we want to incorporate this into the SVS or static VR compensation system into the network, then we have to model it. When we have to understand this, जैसे हमने लोड फ्लो के लिए पावर फ्लो इक्वेशंस लिखा है, एंड पावर फ्लो इक्वेशंस को न्यूटन रैप्सन मेथड में वी नो हाउ टू सॉल्व इट, उसी तरह हमें इसकी भी पावर फ्लो इक्वेशंस लिखना पड़ेगा. We have to write the power flow equation, and then we have to apply that Jacobian matrix, so that, because it cannot be simply assumed as a simple constant PV bus like a generator bus. So let us understand, to model the static VR compensation system, let us understand it, the characteristics. So to understand the characteristics, let us have this static VR compensation means all the system. This is the all complete system. This entire system can be considered as a Z Thevenin's across this load bus. Let us have this middle bus at which the SVS is connected, static VR compensation is connected. We can say SVC bus. So at this SVC bus, let consider the entire network as a Thevenin's equivalent. We know how to convert any network into Thevenin's equivalent. So across this bus, seen from this side, seen from this bus voltage, see the entire system, and find the Thevenin's voltage, then that will be Thevenin's voltage, and equivalent impedance seen from this bus M will be Thevenin's impedance. So this let us consider the SVC load. So this can be written as equivalent to like this: Thevenin's voltage, Thevenin's impedance. Thevenin's impedance is, we consider only the reactance, resistance is neglected for some analysis. That's why. So this is equivalent at bus number M above, in the middle of the transmission line where the SVC is connected. If we see the whole network across this middle of the bus, across the SVC bus, then this can be converted as equivalent Thevenin's voltage and equivalent Thevenin's impedance. So like this, and here a SVC is connected. मतलब क्या हुआ, जो हमारा ये नेटवर्क था, whole this entire is represented into Thevenin's voltage, Thevenin's impedance, and this is here a M bus. So like means this is a M bus, here it is M bus. Now depending upon here, that if it is this is equivalent circuit. Now equivalent circuit, it can be capacitive, it can be inductive. If here capacitive is connected, or if it is inductive is connected, if it is inductive connected, then I into Z drop, I into X drop, it will be like this. I into X, it is a system voltage E, IX, here this I into X drop will take place. Here I into X, because X is inductive, so I into JX, this will take place, and this voltage will be here. This is voltage at the middle of the transmission line where the SVC is connected. So voltage here. This is system voltage. Voltage at SVC bus is this. But if it is a capacitive in nature, because SVC can be inductive or capacitive. So if it is capacitive in nature, so it will be I will be leading. So minus J. Here it is a IJ. I will be the multiplied by J complex conjugate. Here it is minus IJ because it is leading. So current will be this, and it will be voltage at mid of the transmission line. The voltage at the SVC bus can be higher than the system voltage. So by controlling this inductive and capacitive, if it is entirely capacitive, then voltage will be this. If it is entirely inductive, voltage will be this. So by controlling this inductance, we can make the voltage from here to here. We can change the voltage of the SVC bus. SVC bus का voltage हम यहाँ से यहाँ control कर सकते हैं. And where? What is on this x-axis? Y-axis there is a voltage, system voltage, and this is the voltage of the SVC bus. And here it is a load. How much load means load of this SVC load. Current in the load means current in the SVC. So if it is lagging on this side, leading on this side, and VYR is the Z. So Z is the slope of this curve. Z means Z, not the Thevenin's Z, but Z of this inductance susceptance. You can say susceptance of SVC, inductance of capacitance ka equivalent susceptance. So this is that amount. And so in this way, now by controlling this value of inductance and capacitance, with the help of the thyristors, we can maintain this voltage. Now, depending upon if the system voltage, by the way, if the system voltage is this, suppose system voltage is here, the E in place of this system voltage is here, like this E, and we want this voltage to be, this is our actual view which we want to counter, and system voltage is this. Then you can see you can obtain here, like from here, means by system voltage is higher, then inductive can be connected. If system voltage is less, then capacitive can be connected, and finally you can maintain the voltage at the SVC bus. In this way, if we write this in this form, if you write this, this is like this, means we can control, this can be capacitive, here it can be inductive, and finally this can be system voltage. System voltage can be this, system voltage can be this, system voltage can be this. If system voltage is this, system voltage is this, and we want to make this as a voltage, then we will apply hello. Are you able to listen now?
Yes, sir.
Yes, sir.
Yes, sir.
सिस्टम थोड़ा सिग्नल का प्रॉब्लम आ गया था, एनीवे तो नाउ अब तक जो कुछ बताया उसमें पूछना है? Do you want to ask something? So in this way, we can maintain, by making it capacitive or reactive, we can maintain this voltage V here. If the system voltage is this, we will do this. If the system voltage is this, we will apply the inductive here, like this. And one difference is there, that when the limit has reached, the Q reactive power is not, reactive power supply means when it is a maximum, capacitive, maximum capacitive rating can be there. It is a maximum inductive, and after that it is a reactive power is not fixed. It depends upon the voltage itself. This is the difference. So anyway, now how to incorporate this while doing the load flow study? So this is, can be, you can say it can be made like this. This is one conventional method. It is auxiliary bus. If you see again, see here, like this. This is a transformer. This is a bus at which SPS is connected. Pardon?
सर वो शेयर कर दो एक बार, वो स्क्रीन शेयर नहीं है.
स्क्रीन शेयर नहीं हो रहा?
नहीं सर.
अच्छा, दोबारा. यस, दिख रहा है?
ओके सर. यस सर.
Okay. So this is a SVC. It is connected here. This is a transformer. So now this can be, you can see this can be represented like this. It is auxiliary bus where this SVC is connected. This is XT transformer minus reactance of the SVC, and this is the kth bus where the SVC is connected. Kth bus where we earlier we have written, this is the SVC bus, or you can say SVC bus. So here SVC is connected, and we can write the equation for SVC here, and P is 0 always. It will maintain the voltage V, 1 per unit. But after that, if it is not able to maintain the 1 per unit voltage, then what is the susceptance? What is the equation for the susceptance? So we have to write the equations first. Equations we have to write for it. So let us have this like this. देखिए, this is the kth bus where SVC is connected and net susceptance means inductor और capacitance को दोनों को combine करके whatever value of susceptance is there, this is that value susceptance. So current drawn by the susceptance of this means it is a SVC. So current drawn by this is the I will be the voltage of this bus is VK, voltage multiplied by susceptance, voltage divided by reactance, or you can say voltage multiplied by susceptance. J it is a not a real part because it is either inductive or it will be capacitive. So let us have it is a inductive. So it is a J B SVC. So it is the current flowing into this. Okay. Now current multiplied by here voltage VK. If you multiply the voltage, it will be the reactive power because it will be only reactive power. Multiplied by here VK, so it will be VK square SVC, or again, so this is the Q, reactive power. Reactive power drawn by this is given by this. Reactive power VK, it is again called as a QSVC. SVC क्यों? It is a reactive power taken by the SVC or reactive power taken from the kth bus. So it is said as a VK, kth bus. This is the formula for this. Now, this you can write VK square by V Q is the reactive power. Q divided by susceptance. Q divided by V susceptance is the VK square. So write it as a minus VK square is equal to this. ये दिख रहा है आपको? थोड़ा सा हल्का लिखा हुआ है. I think you will be able to see it. इसको इससे कोई फर्क नहीं पड़ेगा. View तो
सर कंट्रोल प्रेस करके स्क्रॉल कर देंगे.
अच्छा, चलो एनीवे अभी ऐसे दिख रहा है. तो ये जो आपका था, ये देखिए यहाँ से, ये दिस इज द इक्वेशन क्यू के डिवाइडेड बाई ससेप्टेंस इज इक्वल टू वी के स्क्वायर. इसी को मैंने इसको यहाँ लिखा क्यू के डिवाइडेड बाई ससेप्टेंस इज वी के स्क्वायर. सिंस इट इज ए लिनियर इक्वेशन, so derivative change in qk by change in susceptance, it is the same. So here from here we can write change in reactive power. This change in reactive power is equal to change in susceptance का यहाँ multiply कर देंगे. change in susceptance qk reactive power, और ये देखिए ये फॉर्मूला बन गया. ये जो फॉर्मूला है change in reactive power will be the reactive power multiplied by change in susceptance by susceptance. इसी इक्वेशंस को इसी इक्वेशंस को, दिस इक्वेशन we have written, this equation is written inside this. You see reactive power is 0. Reactive power supplied by this, because here there is no resistance, only inductance and capacitance are there. So del P, change in reactive power will be 0. Change in reactive power at kth bus will be 0. So del Pk is equal to 0 0. Here 0 0 multiply here 0. And change in reactive power at kth bus, here del Qk is equal to Qk. This ये voltage means change in reactive power will be the reactive power and change in susceptance. ये equation आ गया. This. So this is now applied. This is applied here. ये हमारा न्यूटन रिएक्शन का. If you remember, it is a Jacobian matrix. This is the Jacobian matrix of Newton reaction method. Change in, this is the P2, P3, Pn are known value of active power. These are the estimated value of reactive power. These are the known value of reactive power. This is the estimated value of reactive power. Change in delta, change in this. Here, this equation is incorporated. this equation del pk del kth bus, we assume on application of SVC at kth bus, this equation means from here this is the power angle and this is susceptance. इस पर डिपेंड करते हुए we can apply here. One more equation will be added here for reactive power at kth bus. Suppose at kth bus, so Vk, Qk minus Qk0, K is not here. Other than this, say there is one kth bus, so some modification will be done here, and this will be Jacobian matrix will be modified. With this modified Jacobian, we do iteration and iteration again and again. Then we can find the value of power angle and the voltages. In this way, we apply the SVC. Here, while doing this, we assumed that much amount of reactance. Value of reactance will be the as required to maintain the constant volt. VK maintain करने के लिए, constant voltage maintain करने के लिए जितना susceptance चाहिए उसके accordingly firing angle है. We assume this, but now we can further go ahead that a firing angle we have to decide the firing angle, that at this firing angle this much amount of susceptance will be there, at this firing angle this much amount of susceptance, means value of susceptance changes with the firing angle. And if we include the firing angle also in this study, then how the load flow study will be, means exact load flow study will be performed, that we will see. For that, let us again understand the working of SVC. Say, as I told, now the tangent analysis of this has to be understand. This is like this is your firing angle. These are the thyristors, not the diode. The firing angle of the thyristor are changed so as to maintain the value of susceptance here. And the value of susceptance, now the voltage of this was Vk, say it is a sinusoidal voltage is sinusoidal. If and this is inductance, so current flowing into this will be 90-degree lagging or leading. Current drawn by the inductance will be 90-degree lagging. तो इसका फेसर डायग्राम अगर Vk ससेप्टेंस का वोल्टेज Vk है तो इसका साइन थीटा है, तो इसका एंगल करंट का एंगल क्या होगा, cos थीटा होगा. इज इट क्लियर और नॉट? So it will be like this, firing angle. This will be like this. If it is a voltage of the kth bus, then current at kth will be 90-degree lagging. Actually this is not proper. ये आपका 90-degree lagging, ये 90-degree lagging के बाद यहाँ मैक्सिमम होगा, फिर यहाँ पे ये मिनिमम हो जाएगा. ये थोड़ा सा मिस्टेक है, ऐसा बनेगा 90-degree lagging. वोल्टेज का इक्वेशन है kth बस का, ये करंट की ग्राफ है, करंट का सिग्नल है, एंड दिस विल बी 90-degree हियर मैक्सिमम देन मिनिमम, मींस 90-degree लैगिंग होगा वोल्टेज और करंट के बीच में. नाउ डिपेंडिंग इफ द फायरिंग एंगल इज डन हियर, ये 90-degree है ना, इफ द फायरिंग एंगल इज डन, फायरिंग एंगल ऑफ द थायरिस्टर इज डन एट 90-degree, then the complete conduction current will be there. Conduction means thyristor will be conduct for the entire period. So if the firing angle is 90-degree, then conduction angle will be full. पूरा कंडक्ट. If the firing angle increases than the 90-degree, तो conduction आपका थोड़ा ये कम हो रहा है, देखिए. So this is the relation between firing and conduction angle. ये firing angle, if the firing angle अगर 90-degree होगा तो ये पूरा हमारा 90 का बनेगा, ये बनेगा full. Conduction angle means conduction current will flow continuously from year to year. If the firing angle is increased, तो conduction कम होता जाएगा. Conduction कम होता जाएगा, इसका मतलब क्या है? कंडक्शन कम होता जाएगा तो इसका मतलब क्या, करंट की वैल्यू, एवरेज करंट, आरएमएस वैल्यू ऑफ करंट कम होती जाएगी. तो आई आरएमएस वैल्यू ऑफ करंट कम होती जाएगी, इसका मतलब क्या हुआ, ससेप्टेंस की वैल्यू भी कम होती जाएगी. तो दिस इज द मींस फ्रॉम हियर द यू सी दिस इज ए फायरिंग एंगल अल्फा. सो दिस फायरिंग एंगल अल्फा, दिस इज अल्फा, एंड दिस इज फ्रॉम हियर टू हियर इट इज ए पाई, एंड ये कंडक्शन एंगल, हाफ ऑफ कंडक्शन एंगल. Alpha plus sigma by 2, sigma is the conduction angle, this is the pi. So this is a pi. So you can say relation between, or alpha plus sigma by 2 is equal to pi. So you can say pi minus alpha into 2 is equal to conduction angle तो जितना फायरिंग एंगल होगा उसके अकॉर्डिंगली हमारा कंडक्शन एंगल होगा, और कंडक्शन एंगल के अकॉर्डिंगली ससेप्टेंस होगी, ससेप्टेंस के अकॉर्डिंगली, देखिए ये लिखा है, ससेप्टेंस के अकॉर्डिंगली हमारी करंट होगी। तो ये फायरिंग एंगल का रिलेशन है। सो इफ द अल्फा कंडक्शन एंगल विल बी पाई माइनस अल्फा मल्टीप्लाई बाई 2, ये रिलेशन हो गया। और इसको यहाँ ड्रॉ करना चाहें ऐसा, व्हेन द फायरिंग एंगल इज 90 डिग्री कंडक्शन इज मैक्सिमम, ससेप्टेंस की वैल्यू ज्यादा मैक्सिमम होगी। और जब ये फायरिंग एंगल हमारा 180 डिग्री हो गया तो कंडक्शन जीरो हो गया, ससेप्टेंस की वैल्यू जीरो हो गई। तो इस तरह हमारा दिस इज रिलेशन बिटवीन ससेप्टेंस एंड, it is a susceptance, and this is a conduction angle, and this is a firing angle. So this is a relation, and it is from this equation. So current will be I current will be voltage into susceptance, और उस फायरिंग एंगल पे जितना भी कंडक्शन एंगल होगा उसके अकॉर्डिंगली ये ससेप्टेंस होगी। दिस इज रिलेशन I RMS वैल्यू ऑफ द करंट इज इक्वल टू V and voltage V into voltage, and this I RMS value of the instantaneous value of current, this is the formula V by XL cos alpha minus cos omega t, or if omega t is between firing angle to firing angle alpha by 2, अगर इसके बीच में है, देखिए you see firing angle is alpha and alpha plus y by 2, if it is alpha firing angle alpha से लेके और ये अल्फा प्लस इसे, अगर फायरिंग एंगल इसके बीच में है तो ये फॉर्मूला, ये बिकॉज इट इज साइनोसॉइडल, तो ये फॉर्मूला होगा, तो ये फॉर्मूला होगा, अदरवाइज जीरो। So the RMS value of this instantaneous value here in one range, this is the instantaneous value, in another range, this is the instantaneous value. So total current will be given by this equation. So this equation here can be written like this. This is the value of susceptance I by V in this way. Now so now the reactive power, because we know the susceptance in terms of the firing angle. Now we could know the, here we could know current or susceptance in terms of the firing angle. Once we know the susceptance, we know the reactive power. The formula for reactive power will be like this: V XL XC. This is the formula for reactive power. And so change in reactive power, because we want change in reactive power del Q. So this will be by making the derivative del Q by del firing angle. Firing angle में change होने पे ये कितना कैसे change हो रहा है? Del P will be 0 because at the SVC change in reactive power is not there. Only reactive power change is there. So this is the equation. So del Q, this equation for del Q is incorporated here. If the firing angle, we want to make the exact calculation that if the firing angle changes, then how the reactive power changes. So here in the Jacobian matrix in the load flow study neutral reaction method, here del Q, one more equation at the kth bus will be added, and that will be given by this equation. In this way we make the change in the neutral reaction method to incorporate the effect of SVC to obtain the steady state values, to make the steady state analysis. So is there any question? If it is clear, then anyway, this is the